I've decided to review this book from Tony Junalt. It's entitled Statistical Physics, second and enlarged edition. Very beautiful. All physics books, most 99% of the physics books come with a blue colour because that's the colour of physics books, and they come with a blue coating, whereas biology books are green or red. Chemistry books are red. So we'll move on to this book. It contains about Sonny Junald, professor of low temperature physics in Lancaster University. I've been there, and it's got an amazing library. Lancaster University, spent a lot of time there. I did. Acid-free paper, environmentally friendly, published by Springer in Netherlands. First edition 1988, second 95, and reprinted all the way from 96 till 2007 up until now. So the copyrights were 1988 and 1995 and then 2007. The first chapter is about the basic ideas of this fermionic boson Fermi direct statistics chapters, this book. So it gives you a basic idea, fundamental knowledge about what the other chapters will entail. It talks about the macrostates, averaging postulate, distribution dynamics, the micromechanics of the statistical methods, entropy, microstates within the atoms, its interatomic states of the particles. So gluons, gravitons, fermions, bosons, electrons, protons, antiprotons, weak nuclear force, strong nuclear force. And then we move over to distinguishable particles, thermal equilibrium distribution, and then alpha particles, beta particles, a statistical definition of temperature, not the Boltzmann definition, but the statistical, which is linked to Fermi direct statistics, and then calculation of thermodynamic functions. Then the chapter 3 is all about magnetic moments, interatomic magnetic moments that have an impact on the interatomic interactions. Then chapter number 4, 5, 6, 7, 8, 9 are all about gases. So the first is the distribution behavior of fermions, bosons, the microstate of gases. Then it's all about Maxwell-Boltzmann distribution of the behavior of the gases, and it's about diatomic gases, then Fermi direct gases. It also applies to metals, ionized noble gases. And then chapter number 9 is about Bose-Einstein gases, and it's to do with helium 4. And then chapter number 10 is all about entropy and order, chaos, followed by phase transitions. So ferromagnetism, diamagnetism, paramagnetism, order and disorder in the domain distribution, and then you've got two new ideas like statics or dynamics. Statics is to do with things that are exerting force and having an impact without moving, and dynamics is about objects that are having an impact by virtue of their movement. And then we look at ensembles. And then we briefly look at chapter number 13, which is all about chemical thermodynamics, law 1, 2, 3, 4, zeroth law, first law, second law, third law, and then a bit of a debate about the canonical ensemble, ideal gases in that scenario. And then we move over to liquids, like fermionic liquids that are derived from transition metals in chapter 14, and then we extend that idea as to how those liquids can be considered imperfect gases. So it's a bit this is a bit imaginative, which I wouldn't recommend to beginning students. And then the fifth chapter is future perspectives, superfluid states of Fermi direct systems, statistics in astrophysical systems. Does not relate to the book, but then you've got appendices. Appendix A is about counting problems, and then appendix B is about problems with large numbers, and then integrals, constants, like every book does. Every Springer book has a very comprehensive list of constants, and then exercises, answer to exercises, and that's that. Now the preface one of the things I like about the preface is that he's a professor from Lancaster University, and I've spent a lot of time at Lancaster, and the library is lovely and large, and the statistical physics, he says it's not a difficult subject, but I do think it is very difficult because you need to have an understanding of the first order and the second order decay rate equations. And he says that I trust that it'll not be found a difficult book, which it will be, in my opinion. It contains much that a number of generations of Lancaster students studied with me as part of their physics honours degree. The lecture course was 20 hours duration, and I've added comparatively little to the lecture syllabus. A prerequisite is that the reader should have a working knowledge of the basic thermal physics, like zeroth law, first, second, third law, the Q, the U, and the adiabatic, isochoric, isobaric, isothermal changes, entropy, Arrhenius law, and whatnot. And then we move over to the book Thermal Physics by Colin Finn in the series forms an ideal introduction. Statistical physics has 1,001 different ways of approaching the same basic result. I've chosen a rather down-to-earth and unsophisticated approach, okay, without I hope totally obscuring he's writing as though he was talking, which is slightly, not very friendly to people with English as a second language, ESOL. So as a low-temperature physicist, I've always found a particular interest in statistical physics, especially in how the absolute zero is approached. I should not, therefore, apologize for the low-temperature bias in the topics, which, of course, it's all about, one kind of, statistical physics, which is Fermi-Dirac physics, which is all about low temperature sensitivity, low temperature analysis of gases, ionized gases, liquid gases. Without burdening them with any responsibility for my competence, I'd like to acknowledge how much I've learned in very different ways from my first three bosses as a trainee physicist: Brian Pippard, Keith MacDonald, Sidney Dugdale, and then more recently my colleagues at Lancaster, George Pickett, David Meredith, and Peter McClintock, Arthur Clegg, and many others have done much to keep me on the rails. Finally, most of all, I thank my wife Joanne for her encouragement. So that's Miss Dr. Journault, and then he's giving a preface to the second edition. So he talks about some new material having been added, leaving the organisation of the rest of the book unchanged. The new chapters aim to illustrate the basic ideas in three rather distinct and almost independent ways. The book, he hopes, will be useful for university courses of various lengths. Basic general course for physics undergraduates, short introductory courses, and then chemical physics lectures. Now, the preface to revised and enlarged second edition, published in 2007, which is after 13 years of what he published for the second edition. He says this edition is pretty much the same in terms of organisation and the purpose, but there are minor updates and changes to the text. And then he finishes at it, and that's it. He's added chapter summaries to the first 9 basic chapters. So he considers the first 9 chapters to be basic. That's interesting, because I consider the first 2 to be basic. And then he gives a plan, an algorithmic plan. So the algorithmic plan contains equations as anticipated. So assembly of Avogadro identical particles, volume and thermal equilibrium, temperature T. So this is an algorithmic diagram of understanding. And then talks about basic ideas, macrostates, microstates, defining what a microstate is, defining what a macrostate is, the averaging postulate, which is all accessible microstates are equally probable. So it's equiproportional probability distribution for microstates, variability, and then distribution method and outline, counting microstates, average distribution, model example, composite assembly, statistical entropy, microstates, and chapter 2 is now about distinguishable particles, carrying on from chapter 1. little bits of equations here and there was more descriptive than I anticipated. I was anticipating far more maths work than it's given. So it's explaining. So there's one equation, and then he spends a paragraph or two trying to explain it. There we go. That's that. That's good. So graph. Thermal properties of spin depend only on angle divided by theta. Temperature, angle divided by temperature. And that's for a given system universal. So I like the efficient communicative strategies, which are very direct, to the point, adiabatic demagnetization. So I like the direct, without beating around the bush, or repetitively explaining every single thing. So it's direct, to the point, magnetization, thermometry. Lagrange. Gases, density of states. So chapter number 4. So it touches upon Huygens wave theory principle as well. Dispersion relation, that's Newtonian. And then these are the chapter summaries. Very, very useful indeed. Very useful. Quite the gift. Worth your money for the book. Now, this book is not for undergraduates, it's for postgraduates, because here he didn't take the time to explain the fermions. So you better ought to know what fermions are before you begin to read this book. You'll have to use Google quite a lot before you can get to understand the basics. If you want to read this book, you have to have the basic sound foundation of particle physics prior to attempting to read this book. And of course, it's a given that you need to know your maths. Maxwell-Boltzmann, alpha and beta revisited, but in a very difficult manner here. And then the summaries. For chapter number 5, and then we move on to Maxwell-Boltzmann, which is sort of a step back, because it was all Fermi direct up until now, and now they've gone back to linearity, understanding the linear relationship, rather than the extensivity, Gibbs paradox, Gibbs free energy, that is, diatomic gases. Electronic contribution, vibrational contribution, rotational contribution, heat capacity, onset of rotation. So it describes diatomic gas molecule as an independent system. Fermi direct gases, there we go. Simple formula, A equals N over V times H of 2 pi, that's H squared over 2 pi M K Boltzmann, and then T whole cubed under root. Fermi energy. These books deserve to be read. These books ought to be read properly, because if you don't pay attention to the text or the script, it's not worth it. You won't understand much out of it apart from the diagrams. So that's that. A summary again. Chapter number 8, quantum statistics, Pauli's exclusion principle, Fermi energy, Fermi surface, and then conduction band of electrons, liquid helium, Bose, Einstein gases. Funny bosons. Boson is a particle spin 012. So integral, like whole integers. So I'm just going to based on no rest mass, or like a photon gas. Massless gases and black body radiation. Interesting analysis of bosons and black body radiation. Didn't know about the link that existed. Phonons, we know that phonons are particles of sound waves, lattice vibrations. Assembly at fixed temperature. So isochloric, isobaric, isothermal. So that's isothermal assembly. Now it's talking about conduction bands, phase transitions, ferromagnetism with a minus half solid spin, spontaneous magnetization, paramagnetic region, just like diamagnetic, ferromagnetic as well. And that's order disorder transformation in alloys, different kind of alloys. Two new ideas, statics or dynamics. Interesting chapter. Matter and radiation in equilibrium. So that's the typical, this one is the typical formula that I used to play with in A levels. Transitions with electrons, ensembles, ensemble again. So here it's the, is it the summary? No, that's not the summary. So it defines temperature, internal energy, distribution function, fluctuations, that's the flux. And then that's that. And a bit of coaching on number 6, how to answer questions, problem solving skills. And then a bit of guidance on nomenclature. Canonical ensemble, so probability function is canonical. New horizons. Chemical thermal. Chapter 13, the final one I suppose, is about builds on the ideas introduced earlier in the book, notably the idea of chemical potential energy, its relevance to a discussion of phase transitions, and we shall extend the concept of the ensembles here to discuss the grand canonical ensemble and an approach to open systems. The ideas come together to discuss simple chemical reactions and conditions for chemical equilibria. Chemical potential revisited, equation, Gibbs free energy, Gibbs total free energy, grand canonical ensemble, partial derivative, natural log of t, partial derivative n, j plus alpha plus beta epsilon j. Nice. Ideal gases and grand ensemble, derivation of distributions, thermodynamics of an ideal ambient gas, reaction rates, which is moles per dm cubed per second, and then dealing with interactions. That's chapter number 14. So that's a summary. The first paragraph, the summary. Electrons and metals, conduction bands, electronic vibrations, molecular electronic free electrons, electronic acceleration and molecular vibrations, electronic contributions to heat capacity from low temperature experiments. That's C equals gamma T plus beta T cubed. That's, and then interesting. Never thought liquid metals could be assumed to be a Fermi gas. That's very wild idea right there. And then chapter number 15, superfluid states, superconducting states, supercooled states, superconducting states, superfluidity. Now it's a bit of astrophysics right there. So 15 billion years. Stability of stars, stellar stability, stellar hydrodynamics. Fancy names, dry content. As a footnote, it's interesting to ask whether there's any firm observational evidence for neutron stars. Okay. The answer seems to lie in the discovery in 1960 of pulsars. These are objects which emit radio waves and X-rays as well. These pulsars have a period in the range of milliseconds or seconds, or minutes, which characteristic of a particular pulsar. Origin of the pulsars was not immediately obvious, and they were nicknamed Little Green Men. However, it was soon realized that highly dense stars, white dwarfs, and neutron stars must be involved. So it's speculation at this point. When the numbers were put into possible theories, the observational details of the emitted radiation gave convincing evidence that the likeliest candidate for a pulsar is a rapidly rotating neutron star. Such an object will have around it a remnant of electrons and an intense B field, orthogonal to E field, obviously, around about 1 millitesla, which is 100 million Tesla, sorry. Whoa, that is very intense. Like, that's 11 orders of magnitude higher than what Earth has around it. And then okay, now we're moving to appendices. Very short appendices in this particular case. Answers to questions. It seems like a very difficult book. You'll have to use the index quite often and Google quite often as well. Seems like a very difficult book, so tread carefully, I may say so. Thank you very much for staying with me and for watching this review. I hope you learned something. I mean, I wanted to review this book in its entirety. It took me about 22.5 minutes, and I'm glad I was able to manage but yeah, it seems like it might quite be expensive. Not sure how much it costs. Well, yeah. Thank you very much. Cheers. Thank you for watching. I hope you learned something today. And this is the Statistical Physics book from Dr. Tony Junalt, published by Springer. Beautiful cover, very beautiful indeed, and ends with 217 pages, that is. And so it's beautiful, blue color, very nice. And I hope you enjoy reading it. I would suggest only the very serious physics graduate students be able to purchase it, invest your money in this book, because it's not for the faint-hearted, if I may say so. Alright then, thank you very much for your time. Take care, bye now.